Now we had discussed in the my previous lectures that the turbines are those hydraulic machines which convert the hydraulic energy to mechanical energy and finally to electrical energy, whereas the pumps are those hydraulic machines which convert the electrical energy to mechanical energy and finally to hydraulic energy. So here in centrifugal pumps, what happens is that the work is done by the impeller on the water, whereas in turbines the work was done by the water on the impeller. So this is the difference here. So when you have when you when the impeller or the casing, section pipe and the delivery pipe are filled with water, and then you try to when this mass of liquid is made to rotate by an external force, so that the liquid will be thrown away from the central axis of the rotation. So by this, the water from the inner circumference goes towards the outer circumference with a high dynamic pressure head, because of the centrifugal head that is impressed, and this will enable the liquid to rise from a lower level to a higher level. So now when more and more liquid is made constantly available at the center of rotation, a continuous supply of liquid at a higher level may be ensured. So here what we discussed is that the lifting of the liquid is primarily due to centrifugal action, and therefore the pumps are known as centrifugal pumps. So now this is the sketch of where we have, as I told you, that it consists of the following components. So that is the this is known as the impeller, which consists of the backward curved blades. Okay, so now this is the eye of the impeller, so which is the inner circumference, and this will be the outer circumference, and this is surrounded by an airtight casing. Then we have a delivery pipe as well as a delivery wall which takes water to a required height. So then we have what is known as a suction pipe. At the foot of the suction pipe we have the footwall with the strainers. So here you know that there are few definitions that are involved, which is called the section head and the delivery head. So section head is the distance, is the vertical height of the eye of the impeller from the water surface in the sump, whereas a delivery head is the height of the water surface in the delivery tank from the eye of the impeller. So the total of delivery head and the section head is known as the static head or the total head. Here I will discuss more about this component parts. So now, as I told you in the previously, that when the water is made to rotate. Okay, so here so by through an external source, so what happens is the impeller will do work on the water. So here the water will be thrown away to the outer circumference, so hence a centrifugal head will be impressed here, and because of this the centrifugal head that is impressed, so water can rise to the higher level. So when you make available more and more water at the center of the rotation, then we can ensure that the constant lifting of the water takes place to a higher level. So this is what we were discussing about the component parts of centrifugal pump. We have the impeller, casing, section pipe with a footwall and a strainer, and a delivery pipe. So what is an impeller? So impeller is nothing but a wheel or a rotor. So that's what I said. It is provided with a series of a backward curved blades, or or vanes. So it is mounted on a shaft which is coupled to the external source. That's what I said. The external source of energy usually is an electrical motor which will impart required energy to the impeller, thereby making it to rotate. So by making it to rotate, so the work is done by the impeller on the water. Okay, as compared to, as when you compare to the turbine, so in the turbine work is done by the water on the impeller, whereas here the work is done by the impeller on the water. So also we have is a must casing. A casing is an airtight chamber which surrounds the impeller. So it's similar to the casing of what we had discussed in the reaction turbine. So it is designed in such a way that the kinetic energy of water that is discharged at the outlet of the impeller is converted to the pressure energy, so before it leaves the casing, and thus enters the delivery pipe and to a required height. Here, the section pipe is a pipe which is connecting the upper end of the upper is connected at its upper end to the inlet of the pump, or we also called as an eye of the impeller. So that means it's a pipe which is connecting the sump as well as the inlet of the pump or eye of the impeller. So the lower end of the section pipe will be dipped in the section tank or a sump where from which where the liquid has to be pumped or lifted up. So here the lower end of the section pipe, as I discussed, was that we are providing a footwall and a strainer. So here the liquid will first enter the strainer. Why a strainer is provided? The strainer is provided not to keep the debris away from the pump. So then it passes the footwall. Here footwall opens only in the upward direction. So it's a non-return wall or a one-way type of a wall which opens only in the upward direction. So as such, the water cannot go back again to the sump. So it will not allow the liquid to move downwards back to the sump. And delivery pipe is a pipe which is connected to at its lower to the outlet of the pipe. So it is a pipe which is connecting to the outlet of the pump and delivers the liquid to the required height. So near the outlet of the pump there is a delivery valve. It is used for regulating the water or to control the flow of water from the pump into the delivery pipe. So what is the working principle of a centrifugal pump? So the first step in the operation of a centrifugal pump is the priming. So what is priming? So priming is the operation in which the suction pipe, then the casing of the pump, then the portion of the delivery pipe up to delivery water are completely filled with water, so that there will be no air pockets left in any portion of the pump. So it is always observed that the pressure that is generated is always proportional to or directly proportional to the density of the water. So even in the presence of a small air pocket in any portion of the pump will not generate any pressure head in the centrifugal impeller. So therefore, so to dry out these air pockets, so water is filled. So that as such, so when you start the motor, so therefore the impeller will do work on the water so that the enough pressure head is generated. So here the essential it is always essential to properly prime a centrifugal pump before it is started, so that no air pockets is left in the casing of the pump, or maybe in the suction pipe or in the delivery pipe up to delivery valve. Now, after the pump is primed, the delivery valve is still kept closed, and electrical motor is started to rotate the impeller. So now the work is done by the impeller on the water. So this rotation of the impeller in casing with is full of water will produce something like a forced vortex. So that means the water is thrown away from the central axis of the rotation, and that results in the increase in the pressure throughout the liquid mass. So this, as you know, that the increase in pressure is always proportional to square of the angular velocity and distance of the point from the axis of the rotation. Now, if the speed of rotation of the impeller is sufficiently high, so now the pressure in the liquid surrounding the impeller also will be considerably increased. So as you increase the speed, so also your the pressure also starts increasing. And then when now when the delivery valve is open, the water will be made to flow in the radial outward directions, and so start leaving the way to the outer circumference, and then goes with the increased pressure. Now what happens when the water is thrown away from the eye of the impeller? So at the eye of the impeller there is a partial vacuum that is created. Now you know that the water in the sump is at atmospheric pressure, whereas at the eye of the impeller there is a partial vacuum created. You know that water always enters from higher pressure to lower pressure, so thereby the water from the sump goes to the eye of the impeller, replacing the water which is being discharged from the entire circumference of the impeller. So this again when the water is being supplied to the eye of the impeller, again it will be thrown away from the central axis of the rotation, again moves to the outer circumference with the increased head, and now again partial vacuum is created at the eye of the impeller. So again water rushes from the sump, and this process continues, and thus this high pressure of water which has been developed at the outer circumference of the impeller is utilized in lifting of the water to the required height through the delivery pipe. So this is how the working principle of centrifugal pump. So now this is the inlet velocity triangle as well as the outlet velocity triangle. I told you it is an backward curved blade. Here in the previous case, the turbines, it was the rotation we used to write something like this. So now U is in this direction like this. In the previous case, U was in this direction. So now this is the wheel. We have drawn tangent to the wheel. So this is the radial direction, whereas where this is the tangent to the wheel, so this is known as the radial direction. So two radial directions come and meet at this point, so which is known as the center of rotation. You know that the distance to the inner circumference, so this is the inner circumference, this is the outer circumference. So distance to the inner circumference is always lesser than the distance to the outer circumference. So that gives R is equal to d by 2, and that is d is equal to 2r, and d1 is 2r1. So that's how the tangential velocity, that is u, and here u1 is varying. Whereas in a Pelton wheel, the distance to the inlet and outlet was same. So that's the point where u was equal to u1, and also in the Kaplan turbine also u was equal to u1, because distance to the inlet and distance to the outlet from the central axis of the rotation was same. But in the case of a centrifugal pump, since the distance to the central of the inner circumference is different from the distance of center of rotation to the outer circumference is totally different, so therefore the tangential velocity differs. So you can note that always d1 is greater than d. So that's the reason why u1 is always greater than u. So now, we also observed in the parts of a centrifugal pumps where there are no guide vanes. So therefore, the guide vanes will regulate the water at a particular angle alpha. So since there are no guide vanes, so it is assumed that for the best efficiency, the alpha value is taken equal to 90 degree. So therefore, here the water will be entering in the radial directions. So therefore, V will be always in the radial direction. So now, you know that by the time the water hits the vane would have moved with some velocity. So therefore, the water actually strikes with velocity VR, which is entering in the tangential direction to the vane. So now you can observe that, so the vane is moving in this direction, jet is striking in this direction, so therefore the jet has to enter in the radial direction, that is V is equal to Vf. So now we always get a right angled triangle in the case of a pumps at the inlet. So this angle, that is the angle between VR and you know that it is always theta. So therefore here when they say that the angle of vane at inlet is now theta, here beta is always 90 degree. So now this VR1 is always in the tangential direction as we have discussed. So VR1, by the time the water moves out in the tangential direction, the vane would have moved with some velocity u1. So therefore, the velocity u1. So now the jet which we were observing from outside, that jet leaves in this fashion at an angle beta with the direction of motion of the vane. So if this angle is beta, this angle will be beta. So now line joining from tail to tip is always absolute velocity. The component of v1 in the radial direction is vf1. The component of v1 in the tangential direction is vw1. And you know that the angle of vr1 with respect to motion of direction of the vane is always phi. So this phi is known as vane angle at the outlet. Okay, so this is the beta, which is the jet leaves at an angle with the direction of motion of the vane. So now in this case, here at the inlet, in the radial direction it is Vf, so therefore Vw is always 0. So this is what you have to understand about the inlet velocity triangle and the outlet velocity triangle. So this is what I had said, which was discussed in the previous case, and the velocity diagrams are once again written. Now, you know that for the radial inward flow reaction turbine, work is done by the liquid on the runner, which was given by the formula rho AB into VWU plus or minus VW1 U1. Okay, so that's what we said. If beta is less than 90 degree, take plus sign. If beta is greater than 90 degree, take minus sign. If beta is equal to 90 degree, take BW1 is equal to 0. Since in the centrifugal pump it is just reverse of inward reaction flow turbine, so therefore here the water enters at the inner circumference, moves towards the outer circumference. Here in the radial inward flow, water enters at the outer and moves towards the inner circumference. So now here the work is done by the water on the impeller or runner. So but here work is done by the impeller on the liquid. So therefore you can reverse this to inlet can become outlet and outlet can become inlet. So therefore we can write it as rho AB into VW1 U1 plus or minus VW. You know that VW is equal to 0. We know that VW is equal to 0 because here beta is 90 degrees. So therefore the formula becomes work done per second is rho AB into VW1 U1. Now, many a times work done per second is always expressed in terms of work done per unit weight of the liquid. So then you can, if since the work done per second is written like this, rho AB VW1 U1, you can divide by weight per second. So weight per second is nothing but that is specific weight into Q. AV and Q cancels out. This specific weight can be written as rho G. So rho and rho cancels, AV with cancels, so you're left with VW1 U1 by G. So this will be in meter units. So if you want work done per unit weight of water can be expressed in terms of meters of so head of water, so something like VW1 U1 by G. So you can remember in terms of meters units, or you can remember in terms of the power units, that is Newton meter per second. So as I discussed in the previous case that what is there's few definitions that are involved. So section head is the vertical distance of the center of the pump, that is from the eye of the impeller to the liquid surface in the sump, is known as the section head. And also we had the delivery head. So delivery head is the vertical distance of the liquid surface in the tank to which the liquid is delivered from the eye of the impeller. So you can write it this as delivery head. Okay, so this is delivery head. Okay, so this is I shown in the so this is delivery head. So okay, so this is delivery head. So delivery head is the vertical distance from the eye of the impeller to the liquid surface in the tank. So then the static head is always the sum of section head as well as the dynamic delivery head. Okay, section head and the delivery head. Now there is also called the what is known as the manometric head. So as you had the net head in the case of the turbines, here we have what is the manometric head. So manometric head is the head against which the pump is working. So actually, if you design the pump for some static head like HS plus HD, say maybe about 30 meters. So now you know that water enters in the suction pipe, again goes to the casing, and then comes out in the delivery pipe. Suppose there is loss of head of say something like 2 meters. Again again in the impeller maybe 1 meter, and delivery head again maybe some 3 meters. So total 3 plus 2 5 plus 1 6 meters is gone. So therefore we are raising the water to 30 meters. Actually you design the pump for not 30 meters, you should be 36 meters. So when you design the pump for 36 meters, so that means that is the pump against which this head it is working against this head. So now as you start as you throw the water, so there will loss in the suction pipe, the loss in the impeller, so that the 6 meters will go off. So that means that means the water rises for actually for 30 meters. So this is, but actually you have to design the pump for all you have to account for all these losses that is taking place. So that's why this manometric head, which includes all these losses, so that's why the manometric head is actually the head against which the pump is working. So there are various formulas to calculate manometric head. So manometric head, you know that the work done per second per unit weight of water is VW1 U1 by G. Actually, you want to raise the water to HM, but work done per second is, this has to be, but there is always some loss. Suppose if the manometric head is about 35 meters, and actually VW1 U1 here it has to give work done. If there is no losses of head in the pump, actually HM should be equal to VW1. But by the time that water comes out of the casing, so there is some losses of head in the pump, so that's why that actual head will be after deducting the losses, because when the work is done by the impeller on the water, that is the head that is generated, which is VW1, but there are losses that are taking place, so which has to be equal to this HM. So therefore VW1 U1 by G minus the losses has to give H. So you also know that we fit the gauges at the outlet, and also we fit the gauges at the inlet of the pump, so that difference of the total energies will also give the manometric head, so which is the pressure head at the delivery side, whereas the kinetic head at the delivery side minus the section head at the section side, plus the velocity head at the section side. And as I told you that HS plus HD is the actually the total is the total height to which the water is lifted, but there are some losses in the section pipe, there are some losses in the in the delivery pipe, and also when the water goes to the delivery pipe, so there will be an exit loss. So therefore the manometric head can also be written as HS plus HD plus head loss due to friction in the section pipe, plus head loss due to friction in the delivery pipe, plus the exit loss, which is Vd square by 2g, where Vd is the velocity of flow in the delivery pipe. Now coming to the most interesting part is the efficiency. You know that here we have first as the first we give the shaft power. So now when we try to rotate the impeller, so now the work is done by the impeller on the water, so therefore there is work done per second. So there is always there is a mechanical losses that is taking place, so output divided by the input. So input is the shaft power that you give, and output is the work done per second. So if you take the ratio of work done per second divided by the P, that is the shaft power, so you will get mechanical efficiency. Now using this work done per second, the water is lifted to a particular height. So suppose it is lifted to say HM, that is the head against which the pump is working. So if you want to convert to power, then it is WQ into HM. So now if you take the ratio of this WQHM to that is the this is hydraulic energy or water power, that divided by work done per second gives the manometric efficiency. So if you in the turbines it was P by omega QH, here it is here output by input, so that for WQHM divided by P will give the overall efficiency. So this is how the block diagram will enable you to explain the different types of efficiency. So what is mechanical efficiency? Now it is a ratio of power actually delivered by the impeller. So what is the power actually delivered by the impeller? It is work done per second to the power supplied by the prime mover or by the motor, so which is P. So therefore it is work done per second divided by the power supplied to the shaft by the motor. So therefore rho AB VW1 U1 divided by P. So what is manometric efficiency? It is actually, if you write in terms of head, you can write it as manometric head divided by the head imparted by the impeller. So you know that the manometric head is HM, whereas the head imparted in terms of meters is we have already discussed, that is nothing but that is work done per unit weight of water, which is VW1 U1 by G. So, or if you want to write in power units, you can always write in power units multiplying by specific weight into Q. So this is rho AV work done. It is work done per second, which is rho AV. So you know that this is so AV can be written as Q. So rho can be written as specific weight by G. So this comes to the same formula that we had discussed in terms of meters. Yeah. So now overall efficiency is actually power output. The power output, you know that it is WQHM, power output from the pump divided by power input that is given by the prime mover, which is driving the pump. So that is P. So therefore we know that it is overall efficiency is WQHM by P. Now we can have a relationship between overall efficiency, manometric efficiency and mechanical efficiency by writing these definitions omega q hm by p. So you can multiply and divide by work done per second. So therefore we have this WQHM by work done per second is nothing but manometric efficiency, whereas work done per second divided by the the shaft power gives the mechanical efficiency. Therefore, you know that overall efficiency is always manometric efficiency into mechanical efficiency. So again, I have discussed you should know that this is very important. So therefore, the velocity triangles have to be written properly. So this is the inlet velocity triangle, which you know that. So water, for best efficiency, the water always enters in the radial direction. Okay, this is radial direction. So as the water enters, the vane would have moved with some velocity, therefore it enters the tangential direction. So VR is always in the tangential directions. So this is always in the radial direction. So V is always in the radial direction. Okay, so beta is 90 degrees. So this is a vane angle at the inlet. Similarly, it comes out with velocity VR1 in the tangential direction. So the vane would have moved with velocity U1. So this is actually the jet leaves in this direction, that is at an angle beta. Okay, so this angle is beta, so therefore this angle is beta. So line joining from tail to tip is V1. So therefore the angle between the direction of motion of the vane to the VR1 is always vane angle at the outlet. So always note that D1 is always greater than D. So therefore U1 is always greater than. So since the distances to the inner circumference and distance to the outer circumference are totally different, so therefore the tangential velocities at the inner periphery as well as at the outer periphery are different. So few formulas that are involved to solve some problems. So you know that work done per second is always rho AV VW1 U1 because VW is 0. So work done per unit weight of water is given as VW1 U1 by G. We had various formulas for a manometric head, which is given by VW1 U1 by G minus loss of head in the pump. If there is no loss of head in the pump, so this will be equal. So we also have the manometric head as the total energy at the delivery side minus total energy at the section side, and then we also had HM is equal to static head plus the head loss due to friction in section as well delivery pipe plus the exit loss. I also told you about the efficiencies. So mechanical efficiency is work done per second divided by P. Manometric efficiency is WQHM by divided by work done per second. Overall efficiency is WQHM by P. So this is what. So you also know that overall efficiency is mechanical efficiency into manometric efficiency. So these are once again I wrote the formulas. So this is U is equal to pi dn by 60, U1 is pi d1 by 60. So we have a slight change in the discharge formula. So you know that okay, so now you know that here the circumference is pi into d, but the water, okay, so it's entering like this and coming out like this. Okay, so the d1 is the outer circumference. So now here, so because here the water when it comes out, so it is because there are veins has got some thicknesses, so therefore that's the reason. So you have to deduct the thickness. So suppose there are n veins, so n times the thickness. Okay, like this, then multiply by the width which is perpendicular to the screen, so multiply by width, so this becomes the area. So therefore since the flow is in the radial direction, so where the component is VF, so therefore VF, so area into velocity, so this becomes the area. So you know that the usually generally the area that is blocked of veins is expressed in terms of the circumference. So suppose it is expressed as something like 6% is blocked of the circumference, 6% of the area is blocked. So therefore what we write is that, so this is expressed also pi times d1 pi times d1. So it run as something like say 6% is blocked. So 6% of the circumference is blocked. So that therefore k dash times, so pi d1, k dash times pi d1 multiplying by b into same thing you have to write b into f1. So this, Okay, so now B1 multiplying by B1 into VF1 into VF1. So what happens is that pi D1 and pi D1 comes out, so it will become 1 minus K dash. So 1 minus K dash can be written as K. So now if you say that 6% is blocked, so it becomes now pi B1 D1 VF1 and 1 minus K dash is written as K. So if 6% is blocked, then we can write K as 0.94, 94%. So if it is 8% is blocked, then we can write K as 0.92. So like this the formula comes. So therefore the discharge can be written by the formula. Simply it is area into velocity, which is given as K times pi B1 D1 and VF1. Okay. Similarly, at the inlet, we can write it as K into pi into B into D into VF. Okay. So this is how you write the expressions for the discharge. So taking a few problems. Okay. Now the problems are very simple. If you understand the velocity triangles here, so using the velocity triangles we'll be solving the problems. Now the impeller of a centrifugal pump is 300 mm outside. So outside in the sense is D1 always, and inside is the inner circumference is, or I represent as with no suffix, that is D. So therefore the outside diameter D1 is 300 millimeters, whereas the inside diameter is 150 millimeters here, and the impeller vane angles are 30 degrees. The impeller vane angles is 30 degrees, that is the theta, that is theta, and impeller vane angles is 25 degree at the outer circumference, so therefore it is phi. So now the vanes are moving at a speed of 1450 rpm, so n is 1450 rpm. The velocity of flow through the impeller is constant. So when I say impeller, the velocity of flow is constant, then Vf is equal to Vf1 should be equal to constant. So you can determine work done per the work done by the impeller per unit weight of water. So means in terms of meters unit. So you know that work done per unit weight of water is VW1 U1 by G. So what is our aim is to find out VW1, then find out U1 by G, so that gives work done. So now using the velocity triangles that we had already discussed, so since D is given, N is given, you can find tangential velocity U is equal to pi dN by 60, which is 3.14 into 0.15 into 1450 divided by 60 comes to 11.39 meter per second. Similarly, you knowing D1, you can find out U1, so which comes to 22.78 meter per second. Now you can draw the inlet velocity triangle. You know that so V is always in the radial directions. So by the time the water enters here, the vane would move with some velocity. So therefore it always enters in the tangential direction, which is VR. Therefore this angle is theta. So now you know we can find out Vf because we know theta. So what is tan theta? So tan 30 degrees is equal to Vf by U. So knowing U and theta, so we can find Vf. So but it is said that Vf should be equal to Vf1. So therefore Vf1 will also become 6.58 meter per second. Now, using the outlet velocity triangle, we know that the jet leaves in the tangential direction, that is VR1. So by time the vane would have moved with velocity U1. So therefore the jet leaves at an angle beta, which is V1. So therefore the component of V1, the radial direction is Vf1. The component in the direction of motion of the vane is Vw1. So therefore this component is U1 minus Vw1. So now you can write tan phi equals Vf1 by U1 minus Vw1. So from there we can get Vw1. So you know U1, you know Vw1, hence work done per unit weight of water can be calculated, which is Vw1 U1 by G, which comes to 20.13 meters. So this is how you solve the problems given the angles theta and phi. So since the angle theta and phi is given, so we are able to write the velocity diagrams and solve the problems. So again, similar problems to just to find the here again the vane angle at the outer periphery. We have a centrifugal pump which is running at 1450 rpm. So the discharge is given is 110 liters per second. So divide by 1000, you'll get converted to meter cube per second, which is 0.110 meter cube per second. Now the pump is working against head. So whenever it's said like against head, so then the manometric head is given, which is 23 meters. The diameter of the impeller, so whenever they say only diameter of the impeller, it is always the outside diameter. So the outside diameter is d1. So here it is 0.25 and its corresponding width is 50, that is 50 millimeters, which is 0.050 meters. So you have to find the vane angle at the outlet when the manometric efficiency is given. So now since d1 is given, n is given, the first thing is that you find is the tangential velocity u1. So u1 can be determined, so knowing d1 and n, so which gives 18.98 meter per second. So you can also make use of the manometric efficiency because the manometric head is also given. So manometric efficiency is, that is nothing but the head manometric head divided by work done per second per unit weight of water. So which is hm by vw1 u1 by g. So knowing manometric efficiency, knowing manometric head, knowing u1, so you can find out vw1, which is 15.85 meter per second. So since we for drawing velocity triangles we need vf1, so that is got from the formula of the discharge because discharge is given. So q is k pi b1 d1 vf1. So but here since nothing is mentioned about the area blocked by the vane, so we can take k is equal to 1. Suppose they had given something like 8% is blocked, then you could have taken k is equal to 0.92. So knowing discharge, knowing k is equal to 1, so knowing b1, knowing d1, you can find vf1. So therefore vf1 is 2.8 meter per second. So now you can draw the velocity triangles. So hence tan phi is vf1 by u1 minus vw1. So where the vane angle at the outlet is 41.8 degrees. So this is how you solve the problem. Make use of the discharge equation here, make use of the manometric equation, and then write the velocity triangles and solve the problem solve for vane angle at the outlet. So like this, the data given here is that centrifugal pump has 300 mm diameter impeller. So 300 mm diameter impeller in the sense that it is always the outside diameter. So therefore D1 is 0.3 meters and outlet width is B1, which is 0.050 meters. So it runs at 1000 rpm. So it is delivering water against a head of 15 meters. So therefore manometric head is 15 meters. So you know that vanes are set back at an angle or is curved back at an angle of 30 degree, means it is always phi. So phi is 30 degrees. Then manometric efficiency is 92%. So therefore we have to calculate the discharge. So in order to calculate the discharge, we know that it is k by b1. B1 is given, whereas d1 is also given. Only the point is that we have to find vf1. So in order to find vf1, we have to make use of the velocity triangles. So for finding out vf1, we need u1. So that's the reason why we found out u1 as pi d1 n by 60. So that gives 15.71 meter per second. So but since manometric efficiency is given, manometric head is given, so you can make use of the equation manometric head, that is manometric efficiency is hm by vw1 u1 by g. So therefore vw1 can be determined. So now you can make use of, because phi is given, so you can make use of this triangle, so and then get vf1. So therefore tan phi is vf1 by u1 minus vw1. So therefore vf1 can be calculated, which is 3.19 meter per second. So knowing all the quantities, you can put in discharge equation, so you can get discharge as 0.15 meter cube per second. So this is how we solve the problem for the discharge. So here the manometric head is not given, so therefore this problem was taken to see that how to calculate the manometric head. So now here the discharge is given, which is 0.03 meter cube per second. It delivers water to a height, is not against a height of 18.25. So therefore HS plus HD is 18.25 meters. So it is also given that it is the water is taken through a 100 millimeters diameter pipe, which is 90 meters. That means the length of the suction pipe as well as length of the delivery pipe has to be 90 meters. So therefore LS plus LD should be 90 meters. So also it is given that it is 100 mm diameter pipe. So therefore diameter of section pipe and diameter of the delivery pipe is taken as 0.1 meters. So now the friction factor is 0.04, and here you have to find what is the power required to drive this. So shaft power is asked here. So that's the, so for first we have to find what is manometric head. So for that we need velocity for calculating the friction loss. So but the velocity in the section pipe as well as velocity in the delivery pipe are same, so therefore can be calculated by discharge divided by the area. So therefore the velocity in the section as well as the delivery pipe is 3.82 meter per second. Now you can use the formula FLV square by 2GT to calculate the total loss. Here the total loss will be, because the total length is given, so because diameter is also same in both the cases, velocity is also same in both. So when you use the total length, so definitely you will get the total head loss in the section as well as the delivery pipe. So therefore FLV square by 2GT, so you will get 26.78 meters. So now the manometric head is HS plus HD, which was the static head, which is 18.25. You know HFS plus HFD as 26.78 meters, plus the exit loss, which is that is velocity in the delivery pipe square, that is kinetic head in the delivery pipe, which gives us VD square by 2G. So therefore the total manometric head is 45.03 meters. Now you know that overall efficiency, because overall efficiency is given, is WQ, that is specific weight into discharge into manometric head divided by P. So therefore we can calculate P, which comes to 17.67 into 10 raised to 3 watts. So divide by 1000, you will get 17.67 kilowatts. So you know the power required to drive the pump is about 17.67 kilowatts. Here specific weight of water is 9810, okay, Newton per meter cube. This is meter cube per second. This is in meters. So you get in watts. Okay, so you get the answer in watts. Here this is a centrifugal pump impellers an outer diameter. So D1 is given, which is zero point 0.3 meters. Also inner diameter is given, which is 0.15 meters. It is running at a speed of 1200 rpm. So the impellers are set back at an angle of 30 degrees. So phi is given 30 degrees. Here velocity of flow is constant. So therefore Vf is equal to Vf1, which is 2 meter per second. So we have to find velocity and direction of water at the outlet. So that means the absolute velocity at the outlet is V1 and its angle, that is beta. And then also the manometric head has to determine, assuming manometric efficiency is 85%. So blade angle at the inlet. So the vane angle at the inlet is asked, so that is theta. Now using D1 and N, we can find U1. So U1 is pi D1 N by 60, which comes to 18.85 meter per second. You can also find the tangential velocity at the inlet, which is pi Dn by 60, which comes to 9.425 meter per second. So now phi is given and Vf1 is also given. So you can make use of the velocity triangle at the outlet. So tan phi is Vf1 by U1 minus Vw1. So knowing phi, knowing U1, so knowing Vf1, we can find Vw1. So now since the component of V1 is Vf1 and Vw1, so you can find out V1, which is root of Vf1 square plus Vw1 square. So that gives the absolute velocity at the exit. So now you can find this angle also, the angle with which it leaves. So tan beta is Vf1 by Vw1, so that gives beta as 7.4 degrees. Now also manometric head is asked, therefore manometric efficiency is manometric head divided by work done per second per unit weight of water. So therefore manometric head is manometric efficiency into Vw1 U1 by G. So knowing Vw1, knowing U1 and manometric efficiency, we can find manometric head, which is 25.13 meters. But inlet velocity triangle can always be drawn. So because V is always in the radial direction, so this is U. Okay, so now we have in the tangential direction is VR. So this is angle theta. So therefore tan theta is nothing but, because Vf is equal to Vf1 is equal to 2 meters. We know Vf, we know U because already we have calculated. So tan theta is Vf by U. So therefore theta can be calculated. So this is a problem where that a centrifugal pump has to work against a head that manometer is 25 meters, so HM is 25 meters. It is rotating at 850 rpm. So discharge is given, which is 0.25 meter cube per second. Velocity of flow at the outlet. So it is not constant, it's not given. So velocity of flow at outlet is Vf1, which is 2.5 meter per second. Phi is also given, which is 40 degrees. So manometric efficiency is 95%, 0.95. So we have to find diameter of the impeller. So diameter of the impeller in the sense is D1, width is B1. So now since this phi and everything is given, so Vf1 is given, so we make use of the velocity triangle. So what you do is you write tan phi is equal to Vf1 by u1 minus Vw1, but since u1 and Vw1, okay, because d1 is to be determined, so we cannot find these two quantities, so therefore we can find out u1 minus Vw1 by 2.5 by tan 40. So that gives u1 minus Vw1 is 2.98 meter per second. Now you can make use of manometric efficiency, which is hm by work done per unit weight of water. So now since these two quantities again not known, so Vw1 u1 by g can be written as 25 divided by manometric efficiency. Therefore multiplying by g, so you will get Vw1 u1 as 258.16. so what you do is that you take out Vw1 as 258.16 by u1 and substitute in this equation. So when you substitute here u1 minus, instead of Vw1 you write it as 258.16 divided by u1, so 2.9, so you get a quadratic equation here. So you can solve a quadratic equation and get the value of u1. So this is one typical problem where to solve the value of u1, not by pi d1 and by 60, but you have this by various other data is given, because n is not given, so you are not able to calculate u1. N is given, but since d1 was not given, so you are not able to calculate. So that's the reason why we made use of the velocity triangles and made use of manometric efficiency and got u1. So now knowing u1, you can also find out Vw1 if you want. Otherwise you can go ahead with u1 equal pi d1 n by 60, where you can find out d1. So discharge is given, K is assumed to be 1. So B1 is to be determined. D1 is known now. Vf1 is known. So the width at the outlet can be determined, which is 0.08 meters. So this is one typical problem where the values of D1, that is the outlet diameter as well as its width, is to be determined. So I wanted to use the formula for the manometric head. That is the energy at the outlet minus energy at the inlet. So that's for where we have few readings are given, like section gauge readings. So here be careful that it is 120 millimeters of mercury, because water is flowing here, so you have to convert into meters of water. So how to convert into meters of water? Any meters of liquid to convert into meters of water to multiply by specific gravity. It's already a head unit, so therefore since millimeter is a head unit, so therefore it is written as ps by rho g or ps by omega. So that is 0.12 into, because specific mercury, it is in terms of mercury, so you can multiply with specific gravity of mercury, that gives in terms of meters of water. So now here it is, this delivery gauge reading is given in terms of pressure units, so you know how to convert into the head units. So it is P by omega always, so PD by rho g. So therefore 220 into 1000, so what is density of water is 1000 Newton 1000 kg per meter cube, sorry, 1000 kg per meter cube, and g is meter per second square, so you get 22.43 meters of water. So the difference between the delivery gauge and the section gauge is given as 0.2, so that gets added up here. If they were at the same level, then this would have been 0. So earlier when I gave that formula, I had not given this term. So here, since the difference is given here as 200 millimeters, that is accounted here, which is 0.2 meters. So now you can, knowing the discharge, we can always, because it is given in liters per minute, I can divide by 60 and get it in meter cube per second. So velocity in the section pipe is determined, velocity in the delivery pipe is determined by taking corresponding diameters. So diameter of the section pipe is 0.3, whereas the diameter in the delivery pipe is 0.2. So that gives velocity in the suction pipe as well as velocity in the delivery pipe. So now you know the HM is nothing but the total head at the outlet minus total head at the inlet. So that you substitute the values here and get a manometric head. So knowing manometric head, now you can find out overall efficiency, which is given by specific weight into Q into HM. So that is 9810 into 0.125 into 21.65. So here power is given, which is the shaft power is 40 kilowatts. So don't forget to multiply by 1000 to convert into watt, because the numerator is in watts. So therefore overall efficiency is 66.4 percentage. So this is a problem where we have a three-stage centrifugal pump. So three stages means there are three impellers which are mounted on the same shaft. So whatever the water that flows from one impeller goes will be driven with some particular head, and then goes through connecting passages, goes to the second impeller. Again, it will be thrown with increased head. Like this, when it comes out of the third impeller, again it will be of the more increased head. So for example, for each impeller it throws about 30 meters, so three times that, so that means total it will be 90 meters will be the head. Like this we get increased head, but the same quantity of water is flowing in each of the impeller. So this thing you have to know before we go and solve the problem. So now here it is given as the impeller is D1, which is 40 centimeters, which is zero point 0.4 meters, where the width is given at the outlet, which is B1, which is 0.02. Vanes are curved back, that is phi is 45 degrees. Here reduce the circumference. So this is the first time I am giving circumferential area by 10%. So that's what K factor comes here. So the earlier case I took it is 1. So since it is given as 10% reduction, so therefore K we are taking as 0.9. Manometric efficiency is 90%, 0.9, and overall efficiency is 80%. We have to find what is the head generated, so it is HM, and also we have to find the what should be the shaft power. So you know that where the pump is running at 1000 rpm and delivers 50 liters per second. So Q is 0.05, divide by 1000, you will get 0.05 meter cube per second. So since Q is given, so we can use K by B1 D1 to BF1. So here Q is known, K is also known here, okay, pi, and B1 is also known, D1 is known, so we can find BF1. So knowing BF1 equals 2.21 meter per second. So since D1 and N is given, you can find U1. So and also phi is given, so you can make use of this triangle. So therefore tan 45 is VF1 by U1 minus VW. So that will enable you to calculate what is VW1. Okay. So since VW1 is known, manometric head can be determined. So manometric head is manometric efficiency into VW1 by G, so which gives us 35.98 meters. So since it is head generated here by one of the impellers, so we know that there are three stages, so therefore you can multiply by 3. So therefore total head generated will become 3 times 35.98, which is 107.94. In order to calculate overall efficiency, you have to make use of the total head generated, because it is a three-stage the centrifugal pump, which is a multi-stage pump. So therefore when you write overall efficiency, it is omega q. Here in here it should be total, not one. If you take one, it will go wrong. So that because to drive this three-stage pump we require more power, so therefore here the total head has to be taken. So therefore overall efficiency is for the entire multi-stage pump, so therefore 0.8 here total head has, but q, why it is 0.05, because the same discharge is passing through each of the impeller. So therefore whether you take multi-stage or the one impeller, it will be the same, because the same discharge is passing through all the three impellers. So therefore Q is 0.050 and total head is 107.94. So therefore we can calculate what is the shaft power, which comes in watts. So they will divide by 1000, you will get in kilowatts. So 66.175 kilowatts. So those were the problems that were particularly related to the centrifugal pump, which was, if you know the velocity triangles both at the inlet and the outlet, you can always find all the parameters that are associated with the centrifugal pump. So this particular topic becomes very important, because we have what is known as a minimum starting speed of a centrifugal pump. So when you know that the pump here in the case of a pump, that means the casing or the impeller or the delivery pipe or the suction pipe is filled with water, and then you start the pump, and then water is thrown from the eye of the impeller. So something like a forced vortex type of motion is created, that is, there's a forced vortex is created. So that means here the pressure the pressure head is generated at the outer circumference. You know that the pressure head is proportional to the directly proportional to the angular velocity and the distance distance of the point distance of the point. So therefore here you know that it is always that is proportional to v square by 2g, where v is equal to omega into r. So that is omega by omega into r is nothing but u. So that's why we have the formula u square by 2g. So that's the outlet, it is u1 square by 2g, and the inlet is u square by 2g. But now when the pump is started, this the flow of water will take place only when the centrifugal head that is created. You know that centrifugal head that is created has to be more than the manometric. So when it can overcome such, because the pump has to work against this head. So when this head has to be more than the centrifugal head is more than the manometric head, then the flow will start commencing. So that's the point here. So the flow will commence only when the difference of the centrifugal head that is between the outlet and the inlet has to be greater than the manometric head. So therefore we have the formula u1 square by 2g minus u square by 2g should be greater than or equal to hm. So now the limiting value is equal to hm. So therefore substitute u1 as pi d1 n by 60 and u as pi d n by 60, taking out pi square n square by 60 square outside, and then we get pi square n square by 60 square into 1 by 2g multiplied by d1 square minus d square should be equal to hm. That gives this formula. So therefore we can always express manometric rate by means of the manometric efficiency. So manometric efficiency is hm by work done per unit weight of water. So that gives n manometric efficiency to vw1 u1 by g. Substitute here, so that you get this. So you have this formula. So instead of u1 you write as pi d1 n by 60. So my 1 pi gets cancelled out, 1 n gets cancelled out, 60 gets cancelled out, 2g gets only g gets cancelled out, you are left with 2. So 60 into 2 is 120 into manometric efficiency into vw1 and d1 divided by, so pi into d1 square minus d square is the formula. So this will be the starting speed or a minimum speed. Then only when it achieves this particular speed, then when the flow takes place, or the flow will commence in the centrifugal pump. So we'll solve some problems, one or two problems. So the very simple way of solving the first problem is that we have the diameters of the impellers are given at the inlet and outlet is given. You know that d1 is 0.6 meters whereas d is 0.3 meters. So that will enable us to calculate u and u1. So u is pi dn by 60. Okay, so which is pi dn. So where n is unknown, so where we have to find the minimum starting speed. And u1 is again pi d1 n by 60. Again u1 can be calculated in terms of n. So the best way to solve the problem, because we know the manometric head is given, so therefore u1 square by 2g minus u square by 2g is equal to hm. So simply substitute the values of u1 and u in terms of n and then solve it. So you will get, if the speed is around 892 rpm, then the flow will commence. So there are problems like this where we have make use of the velocity triangles, then we can solve the problems. So therefore the diameters of the impellers are given again at inlet and outlet. Velocity of flow at outlet, that is Vf1 is given, and the vanes are set back means phi is given. You have to find what is the minimum starting speed if manometric efficiency is. So now you can make use of the velocity triangle and use tan 45 is equal to Vf1 by u1 minus Vw1. So therefore u1 minus Vw1 is equal to 2, which is 2 by tan 45. But since u1 is pi d1 n by 60, so you can get in terms of n. So substitute this here, so that you will get Vw1 in terms of n. So now we already derived this equation, which is because we know, so the manometric efficiency is given, Vw1 is in terms of n. Okay, so d1 is given, d is given, so only quantity, that is n, can be solved. So therefore n, so then only when you use this equation, it will be very easy for you. So you have to use, don't try to use that u1 square by 2g minus u square by 2g. So from there only we have got this already, this equation. You should be able to solve this. That's what I said. If you don't want to remember that particular expression, then you have to as usual, you have to calculate from velocity triangles this Vw1. So once you get this Vw1, then you can make use of this equation. But only thing is, you don't substitute till then. You arrive at this particular equation and then you write this equation. Then you start writing u1 and u, and then instead of hm you write this equation. Then for u1 you write pi d1, don't forget pi d1 n by 60, don't forget to cancel this n 1n 1g like this, and then finally you get this expression. So that same expression we had derived, but if you don't remember this expression, you can start from basics, but only thing is you have to see to that you cancel this values of g 1n like this, okay, and then put it in this equation, then you can solve for n. So this is also you same way you can, so otherwise you can remember the formula. So the last topic will be on the multi-stage pumps. You know that I told you that the here the uh, here head producer manometric efficiency. What is manometric efficiency? It is HM by VW1 U1 by G. So what is manometric head? It is manometric efficiency into VW1 U1 by G. But what is U1? It is pi D1 N by 60. So that means manometric head is proportional to d1 and n. So if you try to increase the diameter of the impeller, or you try to increase the speed of the impeller, so then you can produce more head. But by increasing the speed of the impeller, so or that is the to increase the speed, so that means if you try to increase the speed or you increase the diameter of the impeller, or both can be increased, but by increasing this it causes the effect on increasing the stress on them. So there will be some so because there will be vibrations in the impeller material where you will not be able to take that so much stress. So for this reason it is not possible to produce more head with one impeller. So therefore, if you want to deliver the liquid at some quantity of liquid against a very high head, then you have to go for a multi-stage pump. So then we can go for two or more impellers, which will be connected in the series. So that is done is that in multi-stage pumps we generally consist of two or more impellers, identical impellers, which are mounted on the same shaft and will be enclosed in the same casing. All impellers will be connected in series, so that same liquid passes from one impeller to another impeller through the connecting passages. So when it enters the first impeller, it comes out with with increased head, then goes to the connecting passage and enters the second impeller and comes out with some more increased head. Like this, when it passes through each of the impeller, so there will be the head increase will be more. So that means each impeller will produce the head. So if there are three impellers, each is producing some head like 30 meters, the total head developed will be 90 meters. So when you want the a particular liquid to be sent to a larger head, then we have to have the pumps in series. So here, according to the number of impellers that are fitted to the casing, so we have multi-stage pump called as two-stage, three-stage. If there are two impellers, we call it as two-stage. If there are three impellers, we call it as three-stage, like this. If there are any impellers, then they to be raised to this where if you have n impellers connected at each stage, then the pressure head will be n times the manometric head that is developed by one of the impeller. So therefore, the total head developed is n times hm. So if there are three impellers, so the three times the manometric head developed by one of the impeller. But since same liquid is passing through each of the impeller, the discharge of the multi-stage pump is same as the discharge that is passing through each of the impeller of the series. So that is what you have to do. So as you had the pipes in series where the same discharge is passing, here also in the impellers also the same discharge is passing, but we get more head. So this is what is the sketch is that. So when it passes to the one of the impellers, so comes out with the increased head, goes to the connecting passage, comes to the second impeller with more head, again goes to the connecting passage, like this. So when there are three like there are passing through three stages, so therefore three-stage multi-stage pump, whereas here it is a two-stage multi, there are two impellers which are connected to the same shaft but mounted in the same casing. We also have what is known as a pumps in parallel. So we have already understood that in the multi-stage pumps or pumps in series, they are particularly employed for delivering a relatively small quantity of water against a very high head. But when there is a large quantity of water to be delivered against a particular head or a small head, then it is not possible for a single pump to deliver the required discharge. So when you want more discharge, then we have to go for pumps in parallel. In such cases, what happens is that when two or more pumps are used which are arranged in parallel, so each pump is working separately and will try to lift the liquid separately from a common sum, and it will deliver the liquid to a collecting pipe. And then it will be taken to the required height. So in each of these cases, the pump is delivering the liquid against the same head, and so this arrangement is known as pumps. So the same thing here I have shown here. So this is the sum. So each of the pump is working separately. They are connected in parallel. So this will lift liquid against this particular head. So therefore the discharge is Q1. So it is lifting, this pump is lifting liquid discharge Q2. So now it comes as Q1 plus Q2. Again, if you connect one more pump, it will lift Q3. So you will get total discharge Q1 plus Q2 plus Q3. So like this, if now depending on the number of pumps that are connected in parallel, so you will get the total discharge, which is Q1 plus Q2 to Q1. So here, but each of the pump is working is the same head. So the head remains the same, but the total discharge will be more. As we had the specific speed of a turbine, here is the specific speed of a centrifugal pump. So when you have a model of a centrifugal pump, and that means it's a geometrically similar pump, when you try to work against a head of 1 meter, it will deliver 1 cubic meter of liquid, 1 cubic meter per second, that is discharge as one. Then the corresponding speed that is achieved by the centrifugal pump is known as the specific speed. So what is specific speed now? The specific speed of a centrifugal pump is the speed of a geometrically similar pump when working under a head of 1 meter will deliver 1 meter cube per second of water, is denoted by ns. So for starting for specific speed for the turbine, we started with the power formula. So now since it delivers a liquid, so discharge formula is taken. You know that discharge is area into velocity of flow. So you know you have this formula K pi B D Vf. So since K pi is a constant, so therefore it's proportional to B into D into Vf. But you know that B is always, because B is something like 0.1 times D or something like that. So therefore B is also proportional to D. So therefore B can be replaced by D and make it as D square into Vf. So this is first formula which you have. Q is proportional to D square into Vf. But you know that U is pi dn by 60, so therefore U is proportional to dn. But U is also proportional to root h. So depending upon the speed ratio or something like that, you can write it as U is proportional to root hm. But now you can say that D into n is proportional to root hm by taking these two equations. So since we want D here, so what is D here? So D is proportional to root hm by n. So take this D here and substitute here. Okay, and you know that Vf is also proportional to root hm. So we had already taken in the turbine also, it was proportional to root h. Similarly here also it is proportional to root hm. Now the equation becomes Q is proportional to root hm by n whole square into Vf, but Vf is proportional to root hm. So therefore this it can be written as hm to the power of 3 by 2 by n square. So now taking out the proportionality and introducing a constant, so k times hm to the power of 3 by 2 by n square. Now you can make use of the definition of specific speed. When it is working against a head of 1 meter, so it will deliver 1 meter cube per second. So the corresponding speed becomes specific speed. So therefore you can substitute q is equal to 1, n as ns, okay, ns square. So this head as 1, so therefore you will get k as ns square. So substitute k here and get this equation. Okay, so therefore what is ns square? It is n square q by hm to the power of 3 by 2. Taking square root on both sides, you will get n root q hm to the power of 3 by 2. So in the previous case, in the turbines, we had n root p h to the power of 5 by 4, where that was net head. Here it is manometric head, but it is not 5 by 4, it is 3 by 4. Here q is in meter cube per second. We can also find so as I told you that so when you want to take water to a very larger head, then you have to connect the pumps in like series, where the water enters from one impeller, then the same water enters with increased head to the second impeller, the third impeller, so the total head generated will be the more. So here also we are trying to find out what is the number of pumps that is required to take water from a deep well which is working against a head off. So you have to lift water up to 89 meters. So now all the similar pumps are used, but which are running at 800 rpm. So specific speed is given, which is 25, where rated capacity, that is discharge, is given as 0.16 meter cube per second. So now you can find by the formula, specific speed is n root q hm to the power of 3 by 4. So therefore you know specific speed, you know operating speed, you know q. So therefore the head generated by one of the pumps or the impeller can be determined. So now you know that number of pumps can be the total head divided by head developed by one pump. So therefore we require three pumps. So if you connect three pumps in series, then we can get the total head as 89 meters. So since the head developed by one of the pump is less than the total head, hence the pumps has to be connected in series. There is also one more problem related to this. So we have what is known as a data for a single stage centrifugal pump is given. So that means if you are using one impeller, so what happens? So then here this the operating speed is given, discharge is given, manometric head of that pump is given. So using that you can find out a specific speed. So specific speed is n root q hm to the power of 3 by 4, which q is 270 rpm. So since it is given to find out what is the number of pumps for a similar multi-stage, so same pumps are impellers are taken and made as a multi-stage pump. So therefore if you are using a similar pump, then specific speed has to remain the same. So therefore the data of specific speed is taken because the similar pump is used in multi-stage pump. So but how many pumps do you require is to be determined. So here it is little data is little different because we want to lift 5 meter cube. Here it was 3 meter cube per second, so speed was a little more. So since we are delivering 5 meter cube, so speed is reduced, which is 1500 rpm. So here the total head is 200 meters. So but we want to find out what is the head produced. It cannot be 30 meters, so it can be slightly because we are lifting more water with a lesser speed, so the head has to reduce. So therefore the manometric head that is produced, though it is used similar, but the head produced will be slightly lesser. So that's the reason why, but the specific speed remains the same. Okay, so here because we are using a similar pump, so using specific speed, which is n root q hm to the power of 3 by 4, you can find out what is the manometric head. So in this case the manometric head is 28.74 meters. So therefore the number of pumps or number of stages can be determined because the total head is 200 meters. 200 divided by 28.74 comes to 6.96. So therefore you have to use 7 stages. So that means 7 pumps to lift 5 meter cube per second when it is operating at a speed of 1500